This is the Chapter 19 companion, so let's start with sections 1 through 3 of Chapter 19. The first thing this talks about is terminal voltages in batteries, and I mentioned in class that the way I like to think of it is that a battery has an internal voltage and an internal resistance. Now this isn't a real resistance. This is just something that we use to model it. It's due to the chemical reaction that happens inside the battery. The more current you try to draw from the battery, the smaller the voltage looks from the outside. So there's V internal and R internal, and V terminal, which is what you would get if you put a voltmeter from the positive terminal to the negative terminal of the battery, is equal to V internal, and it's missing this little piece that we were talking about. The bigger the current you draw, the more voltage you use up in the battery itself, and it's not available for the circuit outside the battery. So that's the idea behind V terminal. The book uses EMF here. I'm not going to, and I like to use R internal with a capital R, just to keep things simple. I mean, you can use a subscript to show where that resistance is. This also talked about series and parallel resistors. The way you recognize them is one of the hardest things to understand here. The way you do it is you ask yourself, does all the current that goes through one resistor have to go through the other? So here we go. If that's true, then that means you've got series. So here, let me just... If it's not true, then you have to check, but the question you should ask yourself is, do the resistors have the same voltage on either side of them? And I say resistors, this actually works for anything that you want to know if they're in parallel or series. If they have the same voltage across them, same voltage, then you know that you've got parallel. Alright, if neither one of these statements is true, you've got some weird animal that you need to go and break down into easier pieces that either have pieces that are series or parallel. Alright, just to be complete, this one would have this voltage on the top, some new voltage in between the resistors, and then the same voltage that the other one did at the bottom. So it's because of this extra voltage in between the resistors that these are not in parallel. This one, the top one, has some voltage dropped across it, and the bottom one has a different voltage dropped across it. Okay, it's not necessarily different. If these were identical resistors, they would have the same voltage dropped across them. If they necessarily have the same voltage, meaning if you change the value of one of the resistors and it still keeps the same voltage across them, then you know it's parallel. So the way to add resistors in series is actually quite easy. So the equivalent resistance is just equal to R1 plus R2. If you had 3, you would have R3, and so on. For resistors, the harder one to find the equivalent resistance of is for parallel, which is 1 over R1 plus 1 over R2 plus 1 over R3, and so on if you've got more. So in parallel, this is how you add them, and in series, this is how you add them. Let me show you an example of what I mean by a complicated circuit that isn't completely parallel or completely series, and how you would break that down into manageable pieces. This is actually from problem 85 of chapter 19 in your book. I'm going to simplify things by just saying that each of these resistors has a resistance of 3 ohms. The first thing I like to do is just draw the places that have the same voltage. So those all have the same voltage. These places all have the same voltage. And these places all have the same voltage. So what this helps us see is that there's only one resistor with this voltage across it. It's the 3 ohm, and it's the entire voltage from the battery. In fact, we can redraw that part of the circuit like this. So there I have taken care of this resistor. We'll call it, let's see, 1, 2, 3, and 4. This is resistor 3 right here. Any current that flows through resistor 4, do you see how that total current branches here, but it must flow through resistors 1 and 2 as well. So watch how I'm going to redraw that. Here's resistor 4, and now it branches and goes into resistor 1 and resistor 2, but they all have to come together and flow back into the battery. Okay, so here's 1, 2, 3, and 4. This has already made this problem a lot more manageable, at least in my mind. Now I can see that these two, 1 and 2, are in parallel to one another. And so I'm going to redraw this circuit with a new equivalent resistance that takes care of 1 and 2. In fact, I'm going to call it R12. Here's still 3 and 4. R12, 1 over R12, is equal to 1 over R1 plus 1 over R2. So since both of these are 3, here, hold on, let me just, R12 is 1 over 3 ohms plus 1 over 3 ohms. And once I've done that addition, I need to take the inverse. 1/3 plus 1/3 is 2/3. Invert that, and you get 3/2. So it's 3/2 of an ohm is R12. Now, I don't know if you need this anymore, but I'm going to do it anyway. So the colors show that I've got the same voltage there and here. I have some different voltage on either side of R3 and R4. And I still have this voltage in the middle, in between R12 and R4. What I can see now, though, is that anything that flows through 4 has to flow through this equivalent combination, R12. So what I do is I can just add those up in series. Here we go. Okay, I'm going to call this R124. Getting complicated here. And this is still R3 in here. So I know that R124 is just equal to R4 plus R12 because they're in series. So R12 plus R4, and so let's plug in some numbers. R12 is 3/2 of an ohm, and R4 is, sorry about that, 3 ohms. So this is 1.5 plus 3, that's 4.5 ohms is R124. Now I've got, oh dear, in fact, let me just leave this as 9/2 of an ohm, because pretty soon I'm going to need to take the inverse. Now I've got these two, and if I draw my colors one final time, now I can see I've got these in a parallel configuration. They have the same voltage across them. So I can now redraw my circuit with what I'm looking for, Req for the entire circuit. 1 over Req is 1 over R3 plus 1 over R124. 1 over R3 is 1/3 of a 1 over ohm. Okay, and then 1 over R124 is 2/9 of a 1 over ohm. So let me just come up here. REQ is equal to 1/3 is 3/9 plus 2/9 is 5/9. So it's 5/9 to the -1, which equals 9/5 of an ohm. So now let's talk about Kirchhoff's rules. Kirchhoff's rules are all about keeping track of how voltage changes as you go through a loop of a circuit, and then looking at the junctions where the current can split into two different parts. The loop rule is the first one I was talking about. It's where you do the Captain's log. You basically just keep track of potential differences as you go through different circuit elements until you get all the way back to where you started. Now, it's not just useful for that, because you can do a partial journey and just take one circuit element and go through it. And by doing that, you know the voltage dropped by that one circuit element. The one that you go all the way around is a little bit more useful, because if there are some unknowns in there, for example, currents aren't all known, you can use that equation to find out what the currents are through each branch of a circuit. The first thing to do for both of these rules is to choose some current direction for each branch in the circuit. So it doesn't matter if you're right, you just choose a direction you think the current flows. If it turns out to be wrong, later you're just going to get a negative answer for that current, and that's okay. Then for the loop rule, this is the Captain's log. As you travel through a battery, actually, I'm just going to write these down and then talk through them. So as you go through a battery from positive to negative, you know that you've gone to a lower potential, and because of the way batteries work, you know that it's just equal to the voltage of the battery. On the other hand, if you go from negative to positive, you know that you've basically been lifted up in voltage by plus V. Current flows downhill in a resistor, and so if you go through a resistor with the current, when I say downhill, I mean to lower potential. If you go with the current, you need to subtract the current times the resistance. If you go through a resistor against the current, now you're going upstream, and you know, just like when you paddle a canoe upstream, you're going to a higher height. If you go against the current upstream through a resistor, you know you've gone to a higher height, so you put a positive IR. When you get back to the beginning, you write equals 0 volts, and this is because the loop rule is really just a restatement of the law of conservation of energy. Once you've gone and changed all of these voltages by going through the different circuit elements, you've gone back to the place you were, and you know you're at the same height that you started at, and so you write equals 0 volts. Now this becomes an equation you can solve for unknowns, possibly a current, possibly a resistance, who knows, but it's useful. The other one is the junction rule, and for this you just write down that all of the currents into a junction must equal all of the currents leaving a junction. Let's say you had chosen currents that looked like this: I1, I2, I3 for this junction right here. For this example, you would write all the currents in are I1 plus I3. See how I3 goes into the junction and I1 flows into the junction? And then the current out is I2. Again, the reason for these rules is to be able to write down equations that we can use in order to find unknowns. They might be currents in different parts of the circuit. Once you have these, you may be able to go back and find out what's the voltage dropped across individual resistors. Or maybe you know the currents and the resistances, and you're trying to infer what's the voltage that would cause that. Let's finish up chapter 19. This is 19:5 through 7. and this deals with capacitors and circuits. The first part talks about how to add capacitors in series and parallel. Now remember that to find out if a capacitor is in series or parallel, it's just like for resistors. You could just replace these with capacitor symbols, and you would see whether capacitors are in parallel or series. So if capacitors are in series, there it's like increasing D. Remember, we have epsilon naught A over D. It's like making extra distance between the plates of these capacitors. This is the hard one to do. 1 over the equivalent capacitance in this case is 1 over C1 plus 1 over C2. Whereas for parallel, now you've got the same voltage across each of them. It's like increasing the area of the plates. See how I could move these together and you'd have a bigger area? In this case, CEQ is easy. It's just C1 plus C2, and as many capacitors as you had, you could add. The last part of chapter 19 talks about charging capacitors in circuits where there are also resistors. So let me draw such a circuit. Let's say you've got a switch, you have a resistor and a capacitor, and we'll just give them the generic values R and C for the resistance and the capacitance. When you close the switch, there's no charge on the capacitor if it's initially uncharged. And so at the beginning, the voltage, remember that Q is proportional to the voltage. If there's no charge, there's no voltage. There's nothing dropped across here. So this capacitor cliff is not much of a cliff. It's just kind of like a fault line that could become a cliff, and it's going to become a cliff. We're going to see. So the captain's log, right when the switch closes, would have a jump in potential as you cross the battery, and then you drop all the potential as you go across the resistor. So really the capacitor acts like a wire right when you flip the switch. But that doesn't stay like that for long. Remember, if you look at the charge on a charging capacitor, so I'll put charging because it's different if it's discharging. As time goes by, there's some maximal value that the charge approaches, and it's equal to this. Eventually, all of the voltage will be dropped across the capacitor. You know that because zero current's going to flow through the circuit. And if zero current flows through a resistor, zero voltage is dropped across it. So eventually, all of this voltage will be dropped across the capacitor. So what it looks like is this. You get this exponential rise. It's an asymptotic rise up to this Q max. And Q max is when the voltage is all dropped across the capacitor. If you want to see that in the form of an equation, the Q at any time is equal to the maximum Q you ever see, which is just the capacitance times the battery's voltage, times 1 minus e to the minus t divided by RC. So, bizarrely, to me at least, when you take an ohm and you multiply by a farad, the unit is seconds. And so this RC is one very special time, and it is in seconds, believe it or not, and that's when you get to 1 minus 1 over e of the voltage, which turns out to be about 63%. So 0.63. Now this is not e, the charge on an electron. This is e, the base of the natural logarithm. If that doesn't mean anything to you, just believe me that this is the way it rises. I'm not going to ask you about this, although we'll see something similar when we see half-life, because nuclear reactions follow a same kind of a pattern. If you want to know the voltage, it's just proportional to Q, right? There's this constant of proportionality called the capacitance. And so it will look like the same equation. Now, for discharging capacitors, it is slightly different. So this is charging. If it's discharging, then you get an exponential decay from the maximum down to 0. You asymptotically approach 0. And you have Q max times e to the minus t over RC. Well, that's all of Chapter 19. Basically, the idea is to understand how circuits work. RC circuits are pretty complicated because they change in time. If you have big conglomerations of resistors and capacitors, you now know how to break it down into what is the effective or equivalent resistance and capacitance of the circuit. And once you get all of that, Req and Ceq can be plugged in here, and you can understand any system that involves just resistors and just capacitors.